Okay, here we go. So I did do the first problem of this. Part 1, I did post it, why not? So I'm going to start with number 2. And my gosh, an acid-base question. So now the first question in this free response section, you just did 60 multiple choice questions, although this test only had 50. You did them an hour and a half, you get a 10-minute break. And now you get the free response questions. I'm at the end of my rope too.
There's no respect.
Okay, now. You have the first 3 questions are 10 pointers, and these 10 pointers, a lot of points to be had here. You can't get intimidated. You have to think to yourself, okay, what do I know about this problem? What are they hiding? What are they setting up? We've done so many of them. They're all very similar. It's going to be something brand new. It's going to be some setup that you haven't seen before, but the concepts will be the same. So you have to just kind of unpeel it. Okay? All right, as we're passing Tic Tacs around. Now, the first question is a lot like a question you're going to see. Okay?
Hey, I need these. Don't eat them.
Out of your first 3 questions, you're going to see a lab-based question. You want to say, cha-ching, thank you very much, where they give you data. It could be precipitation analysis. It could be a redox titration. It could be a spectrophotometer. We've done all the labs, okay? So you just got to slow yourself down and say, okay, what are they doing here? What are they asking? It's repetitive. I hope you can see that. There might be something brand new. Don't let it get you down, but there's going to be pieces of this you can do, whether it's converting to moles or not. So in any case, everyone likes these types of questions. So I did this already Wednesday, and I have that posted. Everything I did Wednesday is posted. So let's go on to the acid-base equilibrium problem. This is a classic question that you can expect to see. I don't know. This is the not last year's test, so it's a year prior. So therefore, this might be something that could come up again. But if it's not coming to part 2, you can bet your bottom dollar comes up in the multiple choice. So let's do it. Number 2. So we've got an acid-base equilibrium. I know this is not a strong acid. This is a weak acid, okay? And this is my acid group. This is my carboxylic acid, and this is my conjugate base, okay? And we're equilibrium. Okay, now, so propanoic acid is a carboxylic acid reacts with water. Yes, yes, yes. The pH of the 50 milliliter sample of a 0.2 molar solution is 2.76. I'm going to write this here because that's important. Okay. Talk about mysterious. Yeah, I don't know. He was just there a second. Now, hey, identify the Bronson-Lowry conjugate acid-base pair in the reaction. So as we just talked about, here's my acid. And conjugate means same chemical plus or minus an H. So there's my conjugate base. So there it is. And which one, and then make sure you know which one's the acid and which one's the base. Obviously this is the acid. Okay, it's got the extra H. The base doesn't have it because it was lost to make it. Okay, many ways to understand that. So that's pretty simple. That would be a point for doing that. Okay. So again, that's something we should definitely have down. Bronson-Lowry just means to be an acid, you donate a proton. Notice this would donate a proton to the water. To be a Bronson-Lowry base, you accept the proton. Notice to go in the reverse, the conjugate base would accept the proton to go in the reverse. So that's just some basics there, no pun intended. Okay, yeah.
Pun definitely.
Yeah, you're probably right. I feel bad now, I'm over it. Now, letter B. Now, as I said last time, do not write your answers in between these lines, okay? Make sure you use the space provided, okay?
He did.
I know, I graded his, okay? Now, I'm going to write them between the lines because I'm just tall, but I'll white up some areas. So here's B. Determine the Ka of the acid. Okay. So I'm going to white out some stuff here to make some room. So they want the Ka of the acid. Now the first thing I need to know with Ka of the acid, I need to know the concentration of all the players okay, at equilibrium. So I'm just going to white out some area here, and that should be enough maybe. Now, what is Ka? Well, Ka is going to equal to what? The concentration of my conjugate base, okay, which is going to be CH3, CH2, and you don't have to write all of this, but I'm just teaching the problems, okay, all over my times, can't forget that, H3O plus, because it is aqueous, all over the conjugate acid, which is CH3, CH2, COOH. Okay, notice this represents the concentration of the products over the reactants to their coefficients, all one, but when they're at equilibrium. Okay, all I have right now is I have the initial concentration. So I'm going to need an ice table. All right? So I'm just going to write, for simplistic purposes, here's my acid, HA, which we all know is this conjugate base. I don't have the water in this because it's a liquid, it doesn't apply. And it's a double arrow, and it goes to the conjugate base, which is this guy right here, plus the H plus, which is the same thing as the H3O plus. Now what do I know initially? Initially, I have 0 conjugate base, 0 protons, or H3O plus, they are synonymous, and I have 0.2 molar of the base. They gave me that right here, okay? Now another key to the problem is the pH, because you know the change will be that I'm going to minus X, I'm going to plus X, and I'm going to plus X. And what would happen is if you did not use the pH, you would have two variables, the Ka and this stuff. You have to realize, and this was in a multiple choice question, I believe it was question 50 of one of the 3 that we've covered. You have to realize the pH is the X. What's the pH? The pH is the what? pH is equal to the negative log of the H plus or the H3O plus concentration. So they gave me the pH. To go from a negative log or from pH back to a regular number, how do I do that? Right, how do I do that? Right, I need what the value. So the pH is equal to 2.79. To get back what the H plus concentration is, I go 10 to the negative X. 10 to negative 2.76. Now you guys have your calculators. So I'm going to go second function, that little caret key, negative 2.76. These are the skills you need.
It's 2.79.
Yes, it is. Thank you. So 10 to the negative 2.79. Okay. So this is a 9. Thank you. And this gives me what? 0.0016. We'll stop there. But now what is this? Why did I do that? This is actually the concentration of what? The H plus or the H3O plus. If I was to give you the concentration of H plus, you would do negative log to give me the pH, right? But to go back from the pH to give the actual number, you do 10 to the negative X. That's a very important skill. So my friends in chemistry, we just found X. X is this. That's how much H plus is being gained. That's the pH. Okay, so this is our plus X. Oh, Christmas. Always. So this is going to be plus 0.0016. So is this plus 0.00, not to 0, I didn't say it. And this, of course, is also minus 0.0016. But what do we know? this number is so small, we can do what? So at the end, we have 0.2 minus 0.006, right? But that's insignificant, correct? Then we have 0 plus 0.006, do that math. This is the end of the equilibrium. And then of course we got the same idea here. So what do we know, party people? The pH, and this is important, the pH told me the value of my compounds at equilibrium. So now, I'm going to solve for Ka. I'm just going to plug them in. And let's do that. So I take my 0.0, Christmas in this program does it this way. So I take my 0.016, 0.0016, square it, or just times it by itself, all over 0.2. And that's our K. So square that, or in my calculator, divide by 0.2. Okay, and I get my Ka, and this would give you 3 points, by the way. Ka is equal to 1.32 times 10 to the negative 5. They give you 3 points. I forget what the 3 points are. I think they give you 3 points for recognizing that the pH will give you the X. They'll give you the point maybe for putting it in the Ka and solving for it. But I think 3 points are given here. Okay? This is something we've done before. Okay? All right. So the Ka is about that. All right. So weak acid. Okay. Now, kind of a weird kind of couple questions that follow here. Now that's just true and false with explanation. So the next part of this says true and false and explain. I don't have the it's not longer there because I think I erased it, but is true or false and explain why. So here's I. The pH of the solution prepared by mixing 50 milliliters of the sample of 0.2 molar of that weak acid with 50 milliliters of the same concentration of base is 7. So what they're saying is if I titrate this, is this to its endpoint? If I use 0.2 molar of the weak acid and 50 milliliters of it, with 0.2 molars of the weak acid, of the strong base and 50, am I at the equivalence point? Yes. Is the pH 7? No. Okay, so you would say false.
That's it.
No, you have to explain why. Because they're not going to let you just guess. So this will be a point with an explanation. Okay, now why? Okay? Well, what would it look like, guys? What would it look like? You've seen this drawn for you a million times. Of course, we've done it too. This pH would be about above 7, like a pH of 8, or 8 plus, or above 8. Why? If I have a weak acid, like HA, and I have a strong base, like OH minus, at equivalence point, do I have any HA left? No, I've driven it all forward. There's no equilibrium here. This is complete completion reaction. I'm going to make water because this is going to pull the H away. But what else am I going to make? A conjugate base. You've made 100% conjugate base. If it's a weak acid, that means its conjugate base has ability to do what? Ionize water. So this conjugate base is going to yank an H and what? Produce hydroxides. So many ways to say that. The reason why the pH will be above 7 is that in this neutralization reaction, we would create a conjugate base that has an ability to pull an H from water to produce a hydroxide. I don't know exactly how they worded it, okay? I'm using just that stuff. So the key of the question would say, and again, many ways to skin a cat here. I go navel up. I like cats. So they said the conjugate base of a weak acid undergoes hydrolysis. Hydrolysis means a fancy word for just splitting water up into hydroxides. Okay? But I like to say, so the other saying is the conjugate base has an ability to grab an H from water to produce the hydroxide. That's all you would need to say there. Okay? But, in my opinion, you're going to get something Monday where they flip the game on you, where they're going to give you a weak base, strong acid. Where would the pH be there? Right, so if I was to draw a scenario where the same kind of thing's going on, okay, weak what? Base, strong acid, okay, then you're going to see something like this, and the pH is going to be less than 7 if this is 7. Okay, now why in that case? Because the weak base conjugate acid that hydrolyzes water and produces H3O+, correct? Okay, just be aware of that. I feel like they're due for that. Okay, so that's why false is. And the reason is you're creating a conjugate base that hydrolyzes water and produces hydroxide, whatever you like to say. Okay, I, Captain. The second one is true and false. If the pH of hydrochloric acid is the same as the pH of the propanoic acid. So if the pH of hydrochloric acid solution is the same as the one, let's say, we used in this exam or this question, then the molar concentration of the hydrochloric acid must be less than the molar concentration. So what they're saying is, and again, write yourself a scenario that makes you understand what's going on. And for me, sometimes in a crazy test, it's really good to draw, okay, a comparative diagram. So here's my strong acid. Here's a great example. Here's my weak acid. We'll just make it HA, as we always do. And what do we know? The pHs are the same. So make the pH 3, make this the pH of 3. What they say? The pH is the same. Okay. Now we know that this is a weak acid. So what does that mean? It barely what? It barely dissociates. This is a strong acid that completely dissociates. If they have the same pH, which really means the same amount of H pluses, there has to be a lot more weak or low amount of the what? We have right, strong acid. So look at the question. If the pH is the same between the strong acid and the strong, the weak acid and the strong acid, then the molar concentration of the acid must be what? It must be lower. It must be more dilute. Because it dissociates more, okay, it can reach a pH at a lower concentration than the one that barely dissociates. So that would be true. And you would say true, and to answer this, you would say, because the strong acid completely what? Dissociates, you need less of it. Okay? Not sure how they worded it, but that'd be totally fine. Okay? You don't have to be word for word what they say. I'm not sure what they said here. True, HCl is a strong acid, ionizes completely. Fewer moles are needed to produce the same amount. It's the same thing we just said. Okay? All right. So that's all that was. And that was a point. And again, you shouldn't be spending a long time on this, but that was a weird kind of a true and false scenario that I haven't seen before. But again, what's the bottom line? It's making you think about strong acid, strong base. They want you to understand KAs. Okay? Complete dissociation and not. Okay, next question. A student given the task of determining the concentration of propanoic acid solution, okay, of an unknown concentration. A 0.173 molar solution is available to use as a titrant. The student uses 25 milliliters of the volumetric pipette to do. So we're doing a titration here. What do they have? They have a base of a current concentration. The student measures out 25 milliliters of the acid to a clean dry flask. So we have a flask with the acid. Looks like we're going to, from a burette, add drops of Jupiter of hydroxides. Okay. After the adding appropriate indicator to the flask, the student titrates the solution with this concentration of the base. So we know the concentration of the base. We don't know the acid. We don't know the acid. Okay. It reaches the endpoint. What does the endpoint mean? Okay. Now let me make this very clear. When we're using an indicator, the color change tells the chemist or the person doing the titration to stop. That ends the titration. The end point is not exactly the stoichiometric equivalence point, correct? It's a little bit different. They could ask you that in part 2. The end point is the color change. And as we've learned, the color change may not be the perfect what? place where the protons equal the hydroxide. So this endpoint is telling me the color change told us to stop. It is almost exactly like the equivalence point, but it's not. It's a little bit off. But because asymptotic lines, or because these lines are asymptotic, the difference between the color change at this pH change and at the equivalence point is almost insignificant, but you should know the difference. Okay, so what they're saying to you is, I know that this is how much of what? Base that was added. All right? Now, calculate the concentration of the acid. I know I don't like doing this, but could you do MV equals MV here? You could, but here's how I would go about business. Look, how many moles of base do I have? I have, okay, so look, I have this amount of base, right? And I have this concentration of base. How can I get moles? For the millionth time, N1. Take my molarity and times it by what? My concentration in liters, which is 0.02052. What's that going to give me? Moles of my hydroxide or base, which by the way is equal to the what? Moles of the H plus. Okay, and I'm going to divide that by the what? How much H plus do I have initially? 0.025 liters because I'm doing a molarity. Essentially, it's the same thing above here. So I'm going to take my 0.173. I like thinking of it that way, I really do. I have to do mindless formulas. Times 0.02052. Okay, this gives me 0.0035 moles. Lagging here. So I get 0.0035 moles. Divide by the new volume. Everyone with me? Okay, and I get a concentration to be 0.14. The molarity of my acid is 0.14. Okay, that's pretty simple. Now here's the question that gets a lot of people. The student is asked to redesign the experiment to determine the concentration of butanoic acid solution instead of the propanoic acid solution. For a butanoic acid, the pKa is 4.3. So they're going to change. This whole problem is based on propanoic acid. Now they're going to do butanoic acid. The pKa, the value of the pKa is 4.83 of the butanoic acid, new acid. The student claims that a different indicator will be required to determine the equivalence point of the titration accurately. Based on your response to part B, which by the way, part B was solving for the what? Ka, is this true? Will we need a different indicator? Now listen, party people, this is the graph we have right here. Okay? They had an indicator that told them to stop the what? To stop the titration because it was probably somewhere on this asymptote, right? But the rule is, okay, the rule is you need to be plus or minus 1 from this position. Now understand this is really important. I'm going to draw this as a color. When you titrate with an indicator, and this is important, they're going to ask this, an indicator is really a weak acid-base pair, isn't it? So when you titrate, you're also titrating the indicator, but you're using only a couple of drops. So listen, the indicator does what? The indicator actually buffers in the position. Yes, it'll eventually, do its thing, but we're trying to have the indicator do what? Buffer in this position, right around plus or minus the equivalence point or the endpoint. So we're looking for a what? If we were looking for the pKa of the indicator, we'd pick one. So all we have to do is see how similar the pKa of the acids are to answer this. So notice this is the Ka. All I'm going to do is do the pKa, which little p means what? Negative log of this. So negative log of 1 point, oh Christmas, 2. I can do this. Maybe not. E to the negative 5. And so when I do negative log of that, I get a pKa equal to 4.87, well, 88, okay? So that is for the propanoic acid. And now they're going to do butanoic acid. Is it similar? 4.83, 4.88. Yeah. So what does that mean? If the pKa's are similar, or the Ka's are similar, that means the strength of the acid is similar. That means it's what? Its equivalence point will be similar. Correct. So therefore, the indicator that they use for the propanoic acid, the first part, is fine. So, do you agree with the student's claim that you need a new indicator? The answer is no, because the Ka's or the pKa's of both acids are similar, which means the amount of dissociation or their equivalence points will also be similar. Okay? That's really all you need to say there. All right, so that's a nice little acid-base problem. Okay? They're constantly asking you why, though, if you noticed. Yes?
If, let's say the pKa for one of them was much, much lower, how would, what would that do to how, which indicator you
If the pKa was lower, that would mean that your curve, instead of, let's look at this one right here. If the pK was here, so let's like, forget, this is my, let me get thicker here. So here's my curve here. Okay, so this is my buffer region where we get the Ka's, right? Okay, max buffer position. If the other one was, let's say, lower, okay, then you would have a different region where the what? Asymptote is, which means you'll have a color change that may be not in that asymptote anymore, which would give you a volume that's significantly different. Okay? The bottom line, plus or minus 1 pKa is what we use for the indicator evaluation, although we're not talking about the indicator. Okay? All right, moving forward. See you guys. Good luck if you're playing today.
We're done.
Are you done for the week?
Yeah.
Sorry. You're leaving. Okay. Yeah, I don't know. Oh, yeah, practice. Okay, number 3. So number 3, and this is something else that I believe you're going to see also. I really believe that there's going to be a electrochemistry question just from looking at last year's test. I haven't seen a lot of this in multiple choice, so you're either going to see this in multiple choice or part 2. That's my guess. I'm not always right in this, but I feel like if I haven't seen it enough, then it's going to pop up. So here we have, and this is important, okay, a voltmeter is not a battery. So you're looking at something called a battery, 2 words for it, voltaic cell, or what? A voltaic cell, or we can say galvanic cell. Luigi Galvani, as Alessandro Volta, were the 2 people that, with their argument of what moves the frog legs, I've talked about a couple times, that's where they give the name to the battery. This is called electrochemical cell, but the one that has a battery is the electrolytic. That's the one where we're plating or taking a what? A non-spontaneous process. So electrolytic cell is what this is not. Okay, this is a galvanic cell. This is spontaneous. This produces a voltage. Okay, so a student is given a standard galvanic cell that gives it away that it's a battery. It has a copper electrode and a tin electrode. Okay, as current flows through the cell, the student determines the copper electrode increases in mass and the tin electrode decreases in mass. Remember, you guys do not have net potential tables anymore. So you could not look, I don't agree with it, but that's what they're doing. So you could, if you didn't have these hints, you wouldn't know who was oxidizing, who was reducing, unless you went to the table and see who had the greatest oxidation potential. But by saying that what? The current flows and that the copper electrode increases in mass. So this is increasing in mass. Now why? What's in the solution? Copper plus 2. And somehow copper plus 2 is becoming copper 0. That only occurs by the reduction, gaining electrons. Electrons in the reactant. So copper aqueous becomes solid metal. That's important. Anytime you see the metal that's at 0, it's solid. Of course, the exception is mercury, but you won't see that. Okay? And that tells me what? The tin on the other side must be oxidizing. The 0 must be losing some electrons. We're going to guess it's 2 electrons because tin has a couple of different oxidation states. Because tin plus 2 and 2 electrons. Reduction is what? Leo, losing electrons. This is gaining electrons. It's got to be clear. And what happens here is a solid what? Tin. I'm going to show it disappearing. Becomes tin plus 2. Great place in the summer.
Oh,
Yeah, I've never been, actually, just sounds fun. Okay, so the electrons are what? Are pushed through the circuit, which will eventually be closed. I guess through the voltmeter it's closed. And these electrons build up, if you want to think of it like that, on the what? Copper, and the copper jumps on them to become copper 0. That's how it works. Okay, identify the electrode at which oxidation is occurring. Okay, then you would say the tin is where oxidation is occurring. So you would say this is where oxidation is occurring, and give your reasoning. You give your reasoning that so many ways to say this, but the tin is the place where electrons come from. If copper is gaining in mass, that means the copper plus ions are getting reduced, which means that the tin has to get oxidized. There's many ways to say this. Okay, explain it based on the student's observation. So again, if copper is gaining mass, that means it's getting reduction. This must be the reduction cell. Then therefore this must be the tin is the oxidation cell. That's where the electrons have to be produced from. So tin has to lose them, and they actually get smaller. They don't say, they just say copper gets bigger, but the tin will have to get smaller. And there they go, letter B. As the mass of the tin electrode decreases, where does the mass go? Well, you could say that it goes to the copper, but remember electrons don't have much mass. Best answer is what? That they become tin what? The mass of the metal becomes what? Tin aqueous ions, right? So we'd say the mass goes into solution. All right, look at your half reaction. Solid metal is going into solution. I'm not sure if they'd accept going into the copper. I go, yes, a little bit of the mass is going that way. Okay. Letter C. In the expanded view of the center portion of the salt bridge, draw and label the particle view of what occurs in the salt bridge as the cell begins to operate. Omit solvent molecules like water. All right. Well, what's happening here? We know that we can't really have a battery or a galvanic cell without a working salt bridge. And what I know in my salt bridge, I have K plus and I have NO3 minus. So I'm going to write that. Now, I have K plus, all right, the plus here, and NO3 minus. I know that this is connected to the what? The tin side. All right, this is going to like jump into there. It's kind of a way to draw it, I think. And then this is going to connect to the copper side, which we know is the cathode side. And again, doing my best that I can. Okay, that goes in there. And then here's my copper. And this is connected to to each other. Okay, now, what's happening? Well, party people, we said the mass of the copper is getting what? Bigger. Because the copper plus 2 in solution is being reduced into pure copper. So in this beaker, we're losing positive 2 ions. We're losing positives. This beaker will get negative if we don't replace the positives that are lost. So therefore, the K plus is going to move toward the copper. In this beaker, solid tin becomes tin plus 2. This is building up of positives in the anode or the oxidation half cell. This is no good either. Electrons will not flow away from a positive beaker, just like electrons won't what? Travel to a negative beaker. So to counterbalance the increase of tin plus 2 as the tin oxidizes, the negative ion travels to the oxidation half cell to keep that beaker electrically neutral. Now we could add more to this, couldn't we? Couldn't the tin plus 2 also go through this? You didn't need to do this, but the tin plus 2 could also come this way to replace the copper, and it does. Something else we should realize, and I don't know if you needed this, but you don't. Both of these solutions are nitrate solutions. If you look on the bottom of the beakers, they're both nitrates. So that means both beakers have what in them? Nitrate ions. Now, so this one has nitrate ions. Who's to say that these don't do what? Also flow. Probably wouldn't jump away out of it. Also flow that way too. They just wanted you to show these two flowing. The positive ion goes to the beaker that's losing the positives to maintain electrical neutrality. And the negative ion is going to flow to the side where you're gaining positives in your half reactions. Really helpful to draw half reactions there. Okay. So that's all they wanted. Letter D, a non-standard cell is made by replacing, non-standard, that means you don't have molarities, replacing the 1 molar solutions of the copper plus 2, that's what the nitrates mean, and the tin plus 2 in the standard cell. Now look at this, with 0.5 molar solutions of both. Okay, the volumes are held constant. Okay, is the cell potential of the non-standard cell greater or less than or equal to? Okay, well, let's think about the overall reaction, because this is really a Chatlayer's process, the Nernst equation when you think about it. But let's do it this way. We had tin. Let's do this in different color. Tin reacted, and what did it produce? Tin plus 2, right? We had copper plus 2, and the other beaker reacting to make pure copper. Okay. Now, party people. This is 0, this is 0. These are solids. Solids and liquids do not what? Apply. So it's all about these two. Now, we made both of these have the same concentration. So the ratio of them to each other, where is it? Is there going to be a shift on this equilibrium? No, they both have the same concentration. So the cell potential, okay, doesn't shift. Now, let's pretend that I'm adding more copper plus 2. Remember this I keep drawing? Stress, response. If I was to increase copper plus 2, wouldn't the response be to lower copper plus 2? And that would be what? Shifting it forward? Wouldn't that produce more voltage if I follow the way of the redox reaction? Yes. But they're keeping these, they're lowering both, but they're both the same. Remember the Nernst equation, wasn't it the ratio of the ions over each other? And it was the natural log of that ratio? These ratios are the same. So there's no shifting. So the voltage is what? The same. So you would say the voltage is the same because there's no shift. We're not making the forward or the reverse more or less spontaneous because there's equal amounts of both of them. Yes?
So if you added more copper plus 2, it would shift to the forward and make it more spontaneous?
Yes, and the voltage would go up. Remember I did that reaction? Remember I did that in class? Where I had a solution and I changed the concentrations? This voltmeter would go up and make more volts if I add more copper plus 2. Copper plus 2 is a reactant. So when you increase the reactants, okay, like Chatlayer's principle, you're going to make the forward reaction more spontaneous because the reaction is going to want to what? Go to equilibrium. So it wants to lower it. okay? And the opposite is also true. If I was to increase more tin plus 2, which is a what? A product, the reactant would be more spontaneous in the reverse and the voltage would have to drop, right? This forward reaction I'm drawing for you is the redox reaction that has to occur to create voltage. Remember, delta G is equal to negative N Faraday's constant, okay, times E0 of cell. The what? I want negative G, right? This volts have to stay what? Positive. They stay positive by going forward. If I'm in the reverse of a galvanic cell, it'll give me negatives. We did the Nernst equation, we can actually calculate that the ratio of these ions are the same. Okay? So that's why that's the answer. I Captain. Both the standard and the non-standard can be used to power an electrical device. Of course, the non-standard and the standard just means what you made with 1 mole and something that's not. Would the non-standard cell power device for the same time, or a longer time, or a shorter time? Great question. They're realizing now that you probably figured out that I has no effect. But isn't there less reactance? Yes. So you could say what? Because you have lowered the what? Now the tin and the copper and the Sn plus 2 have no effect, right? Because this is, but if you lower the tin plus 2 that we just did, okay, there's less of it. So think about it. How does this reaction work? If there's less copper plus 2, this battery is going to stop once we're out of copper plus 2. Don't you realize that? So because now, instead of being 1 molar, it's 0.5 molar, everyone see that the non-standard cell would run out of voltage faster. So there'd be a shorter time. So compare, would the non-standard power the device at the same time, longer time, or shorter time? You would say a shorter time, and justify, because why? There's less amount of reactants. The reactants will run out quicker. It's that simple. As weird as that may sound, that's all that question is about. Anytime they change the concentrations of the ions in a redox reaction, they want to know more or less volts. I want you guys to write the entire redox reaction and just do a Le Chatelier's problem. Am I increasing the reactants? Then the forward reaction goes more, I have more positive volts. Okay? If I make the reverse go, the volts drop. Okay, so letter E. Okay, in another experiment, a student places a new tin electrode into a fresh solution of copper, Christmas in July, in copper nitrate. So this is another experiment. It's not even a galvanic cell. It's not a battery. They have a solution of copper nitrate, which you all know is copper plus 2. And now we're dropping some tin here, right in there. Okay, so the tin is going to, we know the tin is going to oxidize. We know the copper is going to what? Get reduced. Same reactions occur, so the copper is going to plate the tin, correct? All right, so if you look carefully, if I make this get bigger, here is the tin atoms who have electrons. Here's the copper plus 2. The electrons are going to flow to the copper. This is going to become aqueous and leave, and then the copper plates. Okay, now, so, using the information above, write a net ionic equation for the reaction between the tin electrode and the copper. That would be thermodynamically favorable. Okay, we kind of already did all that, because we know that the copper plus 2 is gaining electrons. So they want the what? The net ionic reaction. So we would have tin 0 goes to what? When it gets oxidized, it becomes what? Tin plus 2. Then we have copper plus 2 becomes what? Yeah, it becomes solid copper. Now, I kind of jumped the gun here, but I do know I can check my work by looking at the charges. This is plus 2 on this side, plus 2 on this side. What I probably should do is draw half reactions. Tin gets oxidized, so it becomes tin plus 2 electrons, right? Both sides of a half reaction have to have the same charge. I add 2 electrons. Copper plus 2 has to gain those same 2 electrons, become copper 0. And notice I cancel my electrons. You got to make sure the electrons cancel. I didn't because I kind of just did it in my head too fast. So that's the overall reaction there. Okay, this is the net ion. Okay, notice I have the solids here. I do because I have to balance it. So this is the overall net ion. Notice I don't have the nitrates, right? The nitrates would be on both sides, correct? So this would be a point. Now, using the information, write a net ion equation between the tin electrode and the copper nitrate. That'd be thermodynamically favorable. Justify the reaction is thermodynamically favorable. Now that they gave me what? Net potentials, I'm going to use them. So look, for copper, gaining 2 electrons. That's positive what? Positive 0.34 volts. Now you could have used tin plus 2 or tin plus 2. It didn't matter. I used tin plus 2.
10 plus 4.
I mean tin plus 4, tin plus 2, whatever. Tin buck 2. All right, now, but this is reduction. What do I have here? Oxidation. So what do I do with these reduction potentials? I flip them. We always flip for reduction potentials anyway. So this is going to be what? Positive 0.14. And then I add them together. What do I get? 0.48 volts, correct? And how does this become my proof that this is spontaneous? Yes, Emily.
Right, so you can flip the sign, except if you have to multiply through, that's why you can't multiply by
Right, and when it comes to net potentials, we never multiply through. What I had to do to make sure my half reaction was right is my electrons had to bounce. But I never multiply through by any value because voltages are a pathway. They're not about how many electrons. That'd be current. That's a good question. But they're always going to write these things as reduction potentials. The one who oxidizes, the one who's going the opposite way of how this is written, you have to flip the sign. So this becomes positive in the reverse. And when you do an overall net potential, there's one you're going to have to flip. Right? Everything can't reduce. Something's got to oxidize. So my friends in chemistry, so you would say what? The net potential of my half reaction is positive volts. Positive volts means a spontaneous redox reaction. And if you don't understand why, because delta G is equal to N, negative N, Faraday's constant, E0 cell. Positive E0 cell, which you just get, is going to make this a negative delta G, which is negative. You don't have to say all that. I'm just showing how it works. So you would say positive 4.8 volts means a spontaneous redox reaction. Okay? And now they want you in II, Captain, calculate the what? Value of delta G. That's easy. Okay? Now what's this little n? I haven't seen this in a part 2 in a while, so this is something I think is fair game. Isn't this n the electrons in a balanced redox reaction? Yes. So that would be 2. I'm answering my own questions. Negative 2.
So the N is
The N is the electrons that are balanced on both sides.
okay.
It's the ratio of electrons to individual reactant. So it's the balance. So if you need to have 3 and 3 or 6 and 6, it would be the balanced electrons for each. Faraday's constant is what? 96,500? And now that's coulombs per what? 1 mole of electrons. That's the charge. And then E0 cell we just got, which is 0.48 volts. Okay? And when we do this, it's very simple. I really don't have a denominator. Okay? So I get 2 times 96500 times 0.48. Okay? And what I get, party people that want to go to the party, they just haven't let you here know where they are. Okay, is 92640, and don't forget the negative sign. Now, you may say, how in the world do we get joules out of this? Okay. Now, the key here is that this is coulombs. Coulombs is charge, and this is volt. Now, volt is actually a what? Anyone know what voltage stands for? A voltage is a force per coulomb. So it's joules per coulomb, right? So when you times that by Faraday's constant, which is coulombs per mole of electrons, it goes bye-bye. And notice this is electrons, so you're basically left with just your joules. Now that's important because sometimes you may use this in a thermodynamic equation. You have to recognize that you're dealing with joules, not kilojoules. Okay? So that's the answer in joules. They say include the units because they want to make sure you know it's joules or kilojoules. So this would be joules, or it would be 92.6 kilojoules. You should be aware of our sig figs, probably 0.48, given everything, probably 93 kilojoules. Okay, would be a good significant answer. I'm not even sure they would even look at the significant figures in this question. Yes.
Would still be negative.
And I made a mistake without forgetting the negative again. Yeah. But I maintain the negative. And this again also proves that it's what? Spontaneous. Okay. All right. What do we got left here? All right. Maybe we got time for another one. Now number 5. Did I skip a question?
Thank you.
All right. I guess I skipped 4. Somehow I deleted it, I guess.
These are the 4-point?
These are the 4-point variety. I don't know which one you want me to do. 7, I guess I did 4. Why don't we, it doesn't matter. So, skipping 4, I guess.
Wait,
Nah,
why are we?
because I somehow deleted it. I mean, I could read it and still do it if you'd like, but I'm at the end of my string, so you guys probably are too. Any particular one you want me to do besides 4? Then I'll have it up here.
I would like to see.
Yeah, I have no idea how to do 4.
You want to see 4? Okay. I'll show you 4.